Welcome to AI Paper Slop. Today we are cracking open the paper ESI-Bench towards embodied spatial intelligence that closes the perception action loop. This is fresh research from Stanford, UCLA, and Northwestern, and here are the core insights you need right away. Current vision language models, even the massive ones like GPT-5 and Gemini 3.1, they fundamentally fail at spatial intelligence.
That's right. And they fail because we evaluate them as passive observers.
Exactly. When you actually give these state-of-the-art models an embodied avatar to actively explore a space, their performance jumps because they just spontaneously develop these emergent spatial strategies. But their ultimate bottleneck isn't visual perception at all.
No, it's what the researchers call action blindness. They choose bad actions, and that yields bad views.
Yeah, it creates this compounding cascade of errors. And worst of all, they suffer from a massive metacognitive gap. Humans seek out angles that might falsify their assumptions, right? But these models, they commit prematurely with absolute confidence. They just anchor stubbornly to their first impressions.
So if you are an ML engineer or an AI researcher working on embodied agents or robotics, this paper is going to completely redefine how you need to train and evaluate spatial reasoning.
I mean, to really understand why current VLMs fail so hard in the physical world, we have to look at how we've been testing them up to this point.
Yeah, the illusion of passive spatial intelligence.
Right. The paper argues that spatial intelligence isn't just about what is seen in a static frame. It's about actively uncovering what is unseen. We're talking about occluded structure, physical dynamics, containment, all the stuff you can't get from a flat image.
Which is why they built ESI-Bench. They used the Omni-Gibson simulator and the Behavioral 1K scene pool to create this totally new proving ground.
And Omni-Gibson, for those who don't use it, is a highly accurate interactive physics environment. It's not just a rendering engine.
Exactly. It does rigid body physics, deformable cloth, liquid dynamics. And so they built 10 task categories and 29 subcategories in there. Things like counting objects with occlusion, structural enclosure, view hallucination, liquid volume.
And what's really cool is they grounded this whole framework in cognitive science, specifically Elizabeth Spelk's 4 core knowledge systems.
Yeah, which is fascinating because they didn't just invent ML categories. They went to developmental psychology.
Right. So you have object representation, layout and geometry, number representation, and agents or goal-directed actions.
Spelk's work is basically the blueprint for how infants map the physical world.
Which makes total sense for benchmarking in AI. But I have to say, evaluating a robot using a static data set, it's like testing a human's spatial awareness while keeping them strapped to a chair with their head in a vise.
It really is.
So if cognitive science has always told us perception is a continuous perception action loop, why has the ML field been so obsessed with these passive oracle-style visual observations?
Well, honestly, because passive sensing is just computationally cheaper.
Right, the path of least resistance.
Exactly. If you have a static data set, it is trivial to benchmark at scale. Embodied evaluation in Omni-Gibson requires real-time rendering, physics calculations, action rollouts. It's messy and expensive.
But by doing that, we completely ignored selective sensing.
Yeah, the agent's ability to prioritize task-relevant information over just redundant background noise.
Right. So because passive sensing is so flawed, the researchers didn't just test one method here. They set up a gauntlet of 4 different paradigms to isolate exactly where the models break down.
And those 4 are passive single view, passive multi-view, which gives the model 30 random views, active exploration where it actually moves, and ground truth passive.
Let's talk about the active exploration one, because the findings there are massive. They gave the agents a maximum of 30 steps to move or manipulate objects.
And without any explicit prompting or fine-tuning for robotics, these off-the-shelf models spontaneously discovered emergent spatial strategies.
Which is mind-blowing. Like in the deformable category, to figure out what was under a cloth, the model just learned to grab it and lift it.
Yeah, or to see if a chestnut is inside a glass, it learned to pour it out or maneuver to look top-down. It just figured out how to acquire missing information.
But then you have the failure of the passive multi-view paradigm. And this one really trips me up. They fed the model 30 images, and it often performed worse.
It added noise rather than signal.
Right, but wait, mathematically, shouldn't 30 random views from around a room give you just as much, if not more, data than 30 views you chose yourself? Why does random data add noise instead of context for these models?
It comes down to the signal-to-noise ratio and how attention mechanisms work in VLMs.
Okay.
When you accumulate unstructured views, you are flooding the model's context window. It gets overwhelmed with redundant background pixels, bizarre angles, and contradictory lighting.
So the attention layers just can't align those fragments into a coherent 3D map.
Exactly. It proves that spatial intelligence isn't about giving the model more data. It's about acquiring targeted evidence. One good view inside a cup is worth way more than 30 random pictures of the outside of the cup.
Right, that makes sense. So if models are better when they can control their own movements to get that targeted evidence, you'd think the problem is solved when you give them the wheel.
But it's not even close.
Yeah, not at all. They frequently drive right off the cliff. And this brings us to the core diagnosis of the paper, which is that action blindness dominates perceptual blindness.
Yeah, the ground truth passive paradigm proved this. When they gave the models the oracle views, the exact images, a perfect human trajectory would generate, the models succeed.
So their baseline visual perception is generally fine.
Right. They can recognize the objects perfectly well. The bottleneck is purely in action selection.
And that leads to what they call the failure cascade. Let's say the agent makes a suboptimal action, like it moves backward instead of walking around an object.
And that bad action produces a highly uninformative view, maybe mostly the floor or the ceiling.
Exactly. And because that view is weird, the model's confidence drops, which triggers a worse subsequent action, compounding the error until the 30-step budget is totally exhausted.
The paper has this great specific example. The model is asked, which football is larger?
Oh yeah, I love this one. It starts looking right at a football. But instead of walking forward, the model moves backward, then it looks up at the ceiling, turns down, and just keeps moving forward aimlessly into a wall.
It's just entirely broken trajectory planning.
It's like a Roomba that bumps into a table leg, recalculates poorly, and then spends the next 20 minutes vacuuming a tiny corner of a closet.
Exactly.
But if the model logically knows its goal from the prompt is to compare two footballs, why does one bad view of the ceiling cause it to completely lose the plot instead of course correcting?
Because current VLMs lack persistent spatial constraints and long-term spatial memory.
Right. The working memory is inextricably tied to the visual context window.
Yeah. Human brains maintain a robust 3D scene graph in the background. If we look at the ceiling, we know the football is still on the floor behind us. The models don't have that architecture.
So when the football leaves the frame, their understanding of the room's geometry basically degrades to zero.
Exactly. A single occlusion or misleading perspective permanently corrupts their working memory of the scene.
So as an engineer, if the problem is that VLMs lose track of spatial constraints in flat 2D images, the logical engineering fix would be to just feed them explicit 3D data, right?
You would think so. And the researchers actually tested this.
They augmented Gemini with a VGGT-based 3D scene graph. That's a vision graph generation transformer.
Right, which converts the visual environment into a discrete symbolic map with nodes and edges.
But the results here were highly counterintuitive.
They really were. Explicit 3D grounding does help, but only when the geometry is absolutely perfect. It resolves those depth ambiguities.
But if the 3D reconstruction is even slightly imperfect, it actively misleads the model. It actually performed worse than the flat 2D baselines.
Yeah, imperfect 3D data actively poison the reasoning engine.
It's so ironic. We tried to give the AI glasses, but because the prescription was slightly off, it started hallucinating duplicate objects.
Yeah, that's a great way to put it.
But why is a slightly flawed 3D mathematical graph more destructive to the model than a 2D image that's missing an entire dimension?
Because large language models overly rely on symbolist data. They over-index on text. In a 2D image, the model knows it has to infer things. It expects ambiguity. But in a discrete 3D scene graph, the model treats that text structure as absolute ground truth.
So if the 3D graph has a fragmentation error and says there are two couches instead of one long couch,
the LLM logic pipeline blindly accepts it. It completely bypasses its own visual intuition.
wow. And that leads to massive failure modes like object duplication in enumerative perception tasks. It just overcounts fragments.
Exactly. And you see spatial relation corruption too. If the depth estimate is off slightly, the graph might say two objects are touching. The LLM anchors on that, even if the image clearly shows a gap.
It just refuses to look back at the pixel data to verify.
Right. And this blind trust in corrupted data points to the most profound finding in the entire paper.
The metacognitive gap.
Exactly. It's a fundamental difference in how humans and AI handle uncertainty. The researchers talk about epistemic calibration.
Right, which is basically the alignment between your confidence in an answer and the actual quality of your evidence. Humans treat uncertainty as a signal to keep looking.
But models treat uncertainty as a reason to guess immediately.
Let's contrast human behavior versus model behavior based on the trajectory data, because it's wild. Humans actively seek falsifying viewpoints.
Yeah, active falsification. They intentionally look for angles that might prove them wrong.
Right. If they see something that contradicts their belief, they revise the belief. But models seek confirmation.
They anchor aggressively to their first impression and just move in the same direction repeatedly to confirm it.
The piano example in the paper perfectly documents this. The model starts behind a piano, which just looks like a wooden box from that angle. It guesses cupboard.
Then it moves around to the front, gets a clear view of the black and white piano keys.
And it outputs. Now confirmed it's a cupboard because it has a lot of storage space.
It literally hallucinates a fabricated logical justification to support its initial 1.0 confidence guess.
It completely ignores the physical reality of the piano keys.
Because acknowledging them would conflict with its established token trajectory.
It reminds me of a terrible, stubborn detective. It decides the butler did it in the first 5 minutes. And even when it finds the gardener's fingerprints on the weapon, it says, the butler must be wearing gardener gloves.
That is exactly what it does. And you have to contextualize why this is so dangerous for real-world robotics.
Oh, absolutely. If you put an autonomous agent in a hospital or a warehouse...
Right. A model that doesn't know when it needs more evidence will confidently execute irreversible, dangerous actions.
It's a massive safety issue. And better perception hardware won't fix this.
No, you can give it perfect LiDAR, and if the reasoning engine refuses to update its probabilistic beliefs, it will fail.
Yeah.
We need to train specifically for falsification-seeking behavior.
We have to teach models the mathematical concept of doubt, which really wraps up this deep dive for the ML engineers listening. ESI-Bench proves that scaling up parameters or feeding in more 2D images won't solve embodied spatial intelligence.
The passive era of benchmarking is over.
Exactly. The next frontier isn't just about making models see better. It's about designing architectures that know how to act in order to see and teaching them to doubt themselves along the way.
We have to rewrite the incentive structures of our training pipelines. Right now, RL maximizes reward based on getting the right answer efficiently.
Right. Which leaves you with this specific, lingering question to mull over. We train LLMs using reinforcement learning to maximize reward for correctness. But if our models are fundamentally wired for confirmation bias in physical spaces, how do we design a reward function that actually incentivizes an AI to actively try to prove itself wrong?
That is the structural paradox the next generation of architectures has to solve.
Well, until next time, keep questioning your assumptions.